Hello everyone! In this video we will continue to examine topic 7.2, nuclear reactions, and the relationship between mass and energy. So, Albert Einstein, in the early 1900s, came up with the theory of relativity. And in order to explain fundamentally the relationship between mass, the different definitions of mass we have already seen, and energy, we're going to say at least a little bit about that fundamental theory. It's important to note that a full treatment of relativity is, a full undergraduate level course. If we do the relativity option, which we could choose to do, then you will see more about it there. But this will serve as just the very briefest of intros and show how that idea came to be. Okay. In this video, I'm going to sort of lay out sort of the fundamental aspects of the special theory of relativity. In the next video, I'll talk a little bit about the general theory of relativity, which, as it turns out, will be more directly relevant for our conversation. But it's important that we examine the special theory of relativity first, because the special theory of relativity is sort of A, where relativity really got its name, and B is just a little bit more accessible. It can be discussed and analyzed using mathematics available to y'all if we so chose, whereas the general theory of relativity, properly understood, is written in a mathematical language that it took Einstein himself another 10 years or so to learn. And so we'll come to that in a moment. The first thing to understand is that the special theory of relativity is structured so that it has a couple of postulates. It simply says postulate 1 and postulate 2. These things are true. And then it derives a whole bunch of results. So you take those postulates and you do a whole bunch of math and you derive a whole bunch of results, and then you go out in the world and you see if they're true. So the structure of the theory is like this. We're going to postulate these things, take them for granted, and then, just like in mathematics, derive all these results and then go make some predictions and see if they hold. The postulates themselves, particularly postulate 1, turn out to be shockingly unreasonable. And actually, it's worth discussing that for a moment. So, back in the day, pre-relativity, and in particularly articulated by Galileo, we believed that velocities of objects behaved in the following way. Imagine you're standing on the ground and you throw a baseball or a apple at 5 meters per second. You also have a cart that can move itself at 10 meters per second. If you're standing on the ground when you throw the baseball, you measure the baseball moving at 5 meters per second. But if you stand on the cart and throw that baseball out in front of the cart, and you're on the ground, you will measure that baseball moving relative to the ground at 15 meters per second. If you threw the baseball off the back end of the cart, you would discover that it is moving at 5 meters per second. Now, early in the 1920s, a couple of experiments were done, namely by Michelson and Morley, who, if we cover the relativity option, we'll talk a little bit more about, that showed, or at least sort of it appeared, that light did not do the same thing. At the time, light was not necessarily known to be to work in the way that it does now. And we thought that the electromagnetic waves that constituted light traveled through something called the ether. And we assumed that because, like any other sort of wave, it needed a medium to travel through. And we also assumed that, we would be able to sort of conduct this experiment and figure out how fast we were going around the sun and ultimately in our solar system around the galaxy by more or less conducting the same experiment. There's some details, but the idea is we sent light off in one direction and another relative to the Earth's motion, and we expected to see a difference. And as it turns out, we did not. And so Einstein took this idea, this single idea, this really strange fact that the speed of light is constant and equal to roughly 3 times 10 to the 8th meters per second in a vacuum in all inertial reference frames, okay? In all inertial reference frames. He took it very, very seriously, okay? Now, I cannot stress how weird this single premise is. If we just said it and you sort of thought about it, you would think this is absurd, okay? It's like it's like this person got on the cart with the baseball, threw the baseball at 5 meters per second. They can throw pretty hard off the front end of the cart, and yet someone on the ground still measures that baseball to be moving at 5 meters per second. Not only that, they can turn around and someone on the ground measures that baseball to still be moving at 5 meters per second. Not only that, but they themselves, they're standing on the cart, also measure the same baseball to be moving at 5 meters per second. Okay, that's what is being said about light. That's what premise 1 is. And then premise 2, and this is the relativity part of the special theory of relativity, is that, all right, whatever the laws of physics are, right? We've got to figure out what the details are with this thing. Well, whatever the laws of physics are, they have to be the same, exactly the same, in all inertial reference frames. That is, if we are standing on the cart, I can't have a different physics than if I'm standing on the ground. One important note that I glossed over a little bit, but I should mention, inertial reference frame here just means from a point of view or a perspective where you're not accelerating. So it's important that the comparison we make for Galileo here does not involve comparing when the person is sort of getting on the cart or when the cart is accelerating. It simply involves conducting the experiment either off the cart or on the cart. So it's got to be inertial. It can't be accelerating. And as it turns out, the general theory of relativity is where you can deal with accelerating reference frames. But we're not quite there yet. So given that, all right, there are a lot of not at all obvious consequences. Really absurd consequences. So if you take these to their sort of logical outcome, you derive a number of effects which sound absurd, but as it turns out can be measured and are verified 100 times over. The special theory of relativity is and was on its face absurd when it was published. And it is one of science's greatest successes that we have yet to find an experiment that violates it. In the next video, I'll run through what some of these counterintuitive conclusions were for the special theory of relativity.